Hey guys, this is Tony Bechet, the Physics 2C SI for Dr. Anderson. Today we'll be covering thin film interference. We'll be going over single slit diffraction, and we'll briefly touch on the law of reflection. So let's get started. So when you see thin film interference, always think of the two things that can cause it. So it can be caused by the path length difference, which we've touched upon kind of a lot, and it's caused by the phase shift. So we'll be talking about these two things. Um, so we usually know that the phase shift is caused by maybe the differences in the starting points, right? So that's usually how we've kind of like conceptualized the phase shift. But in terms of thin film interference, it's actually caused by the reflection off of certain media, and we'll touch on that later. But an important thing about this is that the index of refraction is necessary. It's necessary to know the manner in which the light rays reflect. So based on the index of refraction, this will tell us what the phase shift is. So they are related. So more on the index of refraction. This is basically a measure of how fast the light can travel through a medium. And so the index of refraction has no units because it's speed over speed, but it's basically given by c, which is the speed of light in a vacuum, given here, and it's given by the velocity of the speed of light in that specific medium. So it depends on the medium. So in a vacuum, in a perfect vacuum, the index of refraction is equal to 1. Okay? In all other medium, this will be greater than 1. Okay. And why is this greater than 1? Why? Because the speed of light in a vacuum is always greater than the speed of light in any other medium. So because this will be smaller than the speed of light in a vacuum, we're going to have a larger index of refraction. So how exactly is the phase change for thin film interference? How can we understand this? So let's look at a medium here, or rather the border of a medium, and we'll say that here we'll draw two of these. Yeah. So here would be delta x, right? And then this is the medium 1, and this is medium 2. So when light is coming, this is our light ray. It can do two things. It can either be reflected by this medium here, or it can be reflected by this medium here. And we see that there are two different path length differences that are caused by this. Okay, so this is what is important for the phase change. So if we're going from medium 1 to medium 2, and we say that medium 2 is bigger than medium 1, okay, so we'll say that. So this is medium 2 right here. This is medium 1. If the index of refraction for this medium is smaller than this medium, this is going to be reflected with a phase change of pi. So this phase change will equal to pi. Okay, this medium is bigger than this medium. Okay, so if we're going from a phase shift of n2, which is bigger than n1, there's going to be no phase change. Okay, so always keep that in mind. you kind of just have to keep repeating this until you kind of like get it intuitively. But if you're going from something that's weak or weaker to stronger, it kind of intuitively makes sense that it'll reflect because it's like stronger, but it'll reflect with a phase change. So this will give a phase change of pi. The other one will not. So now let's talk about the frequency change between two different media. So the most important thing to keep in mind is that the frequency does not change. It does not change between two different media. Okay, so what is the equation for the velocity of a wave? We have that velocity equals the wavelength times the frequency. Okay, so let's say we have two different media. We know that if the frequency is the same, the wavelength and the velocity will have to decrease or increase to kind of equal each other out. So let's say that the so let's turn this into frequency. So frequency will equal the velocity over the wavelength. Okay, so we can say that. Actually, let me wait on that. So how exactly does this relate? How does this whole thing relate to thin film interference? Well, let me ask you this. What exactly does the index of refraction equal? So we said it earlier. It equals n1. It equals the speed of light in a vacuum over the speed in that medium. So we'll say v1 because it's n1. We know that n2 will equal the speed of light in a vacuum over the speed of light in that specific medium. So how does the velocity change with an increasing or decreasing wavelength? So we know that if the wavelength increases, then the velocity has to decrease. Okay, so if the velocity decreases here, what happens to the index of refraction? It'll have to decrease. So a larger n will give you a larger wavelength, but it also give you slower velocity. Okay, so keep that in mind. The larger the n is, the larger the wavelength will be, but then the smaller, the slower the wave will travel. So how exactly do we get this equation over here? So let's try to derive this, shall we? Let me just erase this. One sec. Okay. So how do we get this in terms of velocity? So we can say that v1 equals c over n1. We know that v2 will equal c over n2. Okay, so let's try to plug this into our equation over here. We get that the frequency will equal either c over n1 over L1, or it'll equal c over n2 over L2. Okay, we know that these are equal to each other because it's the same frequency, which you said over here, because it doesn't change between two different media. So we set these equal to each other, and we get c over n1 over L1 equals c over n2 over L2. And then we can multiply each side by the wavelengths, and we'll get c over n1 times L2 equals c over n2 times L1. Okay, then we can multiply each side. We can divide each side by the speed of light in a vacuum. So this is getting kind of bulky. Let me erase some of this. Let me erase this. We don't need that. Let me move this up here. Let me erase this. Okay, so we can divide each side by c. We'll get L2 over N1 equals L1 over N2. Okay. Now we can multiply this side by N1, and then we can divide this side by, so you can see that. Multiply this side by N1. This side will be multiplied by N1 as well. We can divide this side by L1, divide this side by L1. that'll give us L2 over L1 is equal to N1 over N2, which is basically what we get here. So keep this in mind. Okay, keep these in mind when you're working out the changes in wavelength and the changes in the different index of refractions. So let's go on to single slit interference. So this is kind of similar to double slit interference, but there's some important differences. So the thing to keep in mind is that what we measure here, what we're measuring with this is the angle at which there is a dark slit. So for a double slit interference, we can measure either the light or the dark fringes. The single slit interference, this equation measures only the dark fringes here. So this is pretty, I think this is pretty straightforward. The equation can be either, to find out what the angle is, we can just divide, this, the height of the dark fringe, over the length of the entire screen, which will also equal the wavelength over this width. So keep this in mind because it will be very helpful when you're trying to solve some of the problems I put up in the worksheet. So I think the most important thing to realize with this single slit interference is that the width and the wavelength can both affect the angle. So how does it do that? If we have an increase in wavelength, what will that do to the angle? Okay, and if we have an increase in width, what will that do to the angle? So if we increase the wavelength, we increase the angle. If we increase the width, we're actually decreasing the angle. So the wider that this gets, the smaller that this angle is. The smaller this angle is. We increase that width, this gets smaller. If we increase the wavelength, it has the opposite effect. It increases this angle. So this also works the other way. If we decrease the wavelength, what happens to the angle? The angle decreases. If we decrease the width, the angle increases. So if this width gets smaller and smaller, this angle gets bigger and bigger. Okay, so definitely keep this in mind. This is super important. And just knowing these like the back of your hand will really help you understand how, like, where to go with these type of problems. Okay, so the last thing I want to talk about is the law of reflection. So I know at this point we haven't really gone too much over it in class. We just kind of, just the basics is that if there's an incident ray coming at a surface, then the angle that it gets reflected will equal the angle from the normal. So from perpendicular to the surface, this angle, the angle between the perpendicular line and the incident ray, will equal the angle between the reflected ray and the normal line. So that's something good to keep in mind. And just as a brief, like a little primer for the next lessons, we will see that N1 times the sine of theta 1 will equal N2 times the sine of theta 2. So using this, you can begin to understand the angle that is reflected based on the strength of both of how big both of the indices of refraction are. So we've been doing a lot of variable manipulation. So if this increases, I want you guys to think about this. If this increases, what will happen to this side? If the angle increases, what will happen to this side? So feel free to comment and let me know what you guys think will happen to this. And thank you guys so much for watching. I hold my office hours Tuesday and Thursday from 2 to 3 p.m. And please come by after you do the worksheet and we can talk about all of this stuff in a lot more detail. Thank you guys so much for watching.